What if I told you that a simple string of beads, something you could make right now, holds the key to a really famous piece of math? Well, today that's exactly what we're going to find out. Welcome to Necklace Math for All.
Awesome, because we are about to uncover some, well, mathematical magic that's been hiding in plain sight. So let's meet the star of our show.
Here it is. Our game board is this simple necklace, just a loop of beads. And our whole challenge today is to figure out how many different ways we can color it. Sounds easy enough, right?
Now, to keep things nice and simple, we're only going to use two colors. Every single bead on our necklace can be either red or blue. That's rule number one.
Okay, now for the most important rule of the whole game. We can turn the necklace, or rotate it. And if you can turn one necklace and make it look exactly like another one, then we count them as the same necklace. This one little rule, trust me, it changes everything.
So, this idea of turning and matching, it leads us to a really important idea. If you take one necklace coloring and spin it all the way around, all the different versions you see, we're going to call that a pack. It's a simple name for a really powerful idea.
All right, enough talk. Let's actually put these rules to the test. We're going to start small with our very first case, a simple necklace that has just 3 little beads.
First, let's pretend for a second that we can't turn the necklace at all. So each of the 3 beads has 2 choices, right? Red or blue. That means we have 2 choices for the first bead, times 2 choices for the second, times 2 for the third. That's 2 times 2 times 2, which gives us 8. So if rotation is not allowed, there are 8 possible colorings.
But we can turn the necklace. Now, out of those 8, 2 of them are pretty special. You've got the all-red one and the all-blue one. No matter how much you turn them, they look exactly the same. They're each in a tiny little pack all by themselves.
So that leaves us with the other 6 colorings. And this is where the magic starts to happen. Because 3 is a prime number, those 6 remaining colorings group up perfectly into packs of 3. So you have 2 unique packs, and each pack has 3 different-looking rotations. See how that works? Our total of 8 is just our 2 special ones, plus those 2 packs of 3.
So, how many truly different necklaces are there once you're allowed to turn them? Well, you have the 2 special ones, plus the 2 unique packs. That gives us a grand total of 4. We started with 8 possibilities, but because of our turning rule, there are only 4 distinct necklaces. How cool is that?
Okay, that was super fun. But was that just a fluke? Does this pattern work for other prime numbers? Let's find out. Next up, we'll try a 5-bead necklace.
Now with 5 beads, the number of colorings, if we don't allow turning, jumps way up. It's 2 to the power of 5, which is 32. Whoa, that's a lot more to keep track of.
But does our pattern still work? You bet it does. Out of those 32, we still have our 2 special cases, the all-red and the all-blue necklaces. That leaves 30 other colorings. And since 5 is a prime number, guess what? They group up perfectly into packs of 5.
So let's do the math again. We have 30 colorings, and we're dividing them into packs of 5. That gives us 6 unique packs. Now, add in our 2 special necklaces, and we find a total of 8 truly different necklaces. The pattern holds. Okay, let's test this one more time, super quick, with a 7-bead necklace. Without turning, there are 2 to the power of 7. That's 128 possible colorings. We take away our 2 special ones, leaving 126. And since 7 is a prime number, those 126 must form packs of 7. Well, 126 divided by 7 is 18. So we have 18 packs, plus our 2 special ones, for a total of 20 unique necklaces. And works every time. The pattern is undeniable.
Okay, we've played the game. We've seen the pattern with 3, 5, and 7 beads. So now it's time to reveal the really big idea that we've been uncovering piece by piece.
So what is this secret pattern? I mean, think about it. What did we do every single time? We took the total number of ways to color the beads, we subtracted those 2 special ones, and what was left was always perfectly divisible by the number of beads?
We can actually write this down as a kind of sentence. For any prime number of beads, let's call it p, the total number of colorings, which is 2 to the power of p, is always equal to our 2 special necklaces, plus p times some whole number. And that whole number? That's just the number of packs we found.
And here's the really amazing part. This little game we've been playing with necklaces and colors, it has a secret identity.
You have just visually proven a famous mathematical idea called Fermat's Little Theorem. All that says is that for any prime number p, if you take 2 to the power of p and subtract 2, the answer is always perfectly divisible by p. You didn't need a dusty old textbook, you figured it out just by playing a game.
So you see, this simple necklace game wasn't just a game after all, was it? It was actually a story about a deep, beautiful, and famous piece of mathematics.
The big takeaway here, the powerful trick you just learned, is this. When you have a big, complicated counting problem, look for ways to group things into equal-sized packs. Look for those symmetries. This simple idea, it's at the very heart of how mathematicians think.
And that's really the beauty of it all. Math doesn't have to be boring formulas on a page. It can be a story. A simple game about turning a necklace can explain a powerful theorem. And it's those special, almost magical prime numbers that make the whole story work so perfectly.
So, the next time you're playing a game, any simple game, take a closer look. What patterns do you see? You might just find another beautiful math secret hiding right there in plain sight. Thanks for playing along with me today.